Okay, looks like we're good to go. All right, well, our discussion of division is going to start the same way our discussion of the other operations went, with talking about properties. The first property we'll look at is commutative. And so if we were going to say that 6 divided by 3 is equal to 3 divided by 6, what would you say? True or false? 6 divided by 3 is the same as 3 divided by 6. What do you think? And if you're not sure, you can try it on a calculator and find out. Nope. I agree with you, Nicole. This would be false. This doesn't work. 6 divided by 3 would be 2. 3 divided by 6 would be 0.5. Those are not the same as each other. There is not a commutative property for division. We can't just divide numbers in any order we want. We can multiply them in any order, but we can't divide them in any order we want. All right, well, let's take a look and see if the associative property works. Well, let's see here. If we wanted to do 10 divided by 5 divided by 2, and associative is about grouping, so we change the grouping here. Let's say instead we go 10 divided by 5 divided by 2. Keeping in mind that we always do what's in parentheses first, order of operations. What do you think? Are those two equal to each other? And you can do the calculations and make a decision. 10 divided by 5 divided by 2 is 10 divided by 5 divided by 2. And we'll decide whether that's true or false, whether that's yes or no, to see, can associative work with division? Maybe, I don't know. Here's an example. Let's see whether or not this one works. We don't have any verdict yet. It's a little bit goofy because on the right-hand side, that 5 divided by 2 is going to be 2.5 in there, but still, we can do that. We've got some no's. We've got a no from Moylan. That's good, and a no from Jessica. All right, let's see. So since I started on the right-hand side, let's do that. So then that would be 10 divided by 2.5, which would be 4. And on the left-hand side, 10 divided by 5 would be 2 divided by 2, and that's 1. Since 1 is not equal to 4, this doesn't work. All we need is one counterexample to show false. Associative does not work for division. And then identity property, well, let's see. Is there something I could divide by and have the number keep its value? Just that piece right there. Is there something I could divide by and have a number keep its value? And if so, what would that be? 1. Perfect, Moylan. So if I did 5 divided by 1, I would get 5. So at first glance, we might think, hey, the identity property works. But remember, for the identity property to hold, it has to work both ways, which means I have to also be able to do 1 divided by 5 and get the same number back, and we don't. And so there's no identity property for division either. So no commutative, no associative, no identity for division. Let me know if you have any questions about that. There is one other issue with division that I want to talk over with you. Division with 0. And I guess really division involving 0 would be a better way for me to put this. If we do 0 divided by 4, essentially what we're saying here is I don't have any objects, and I want to divide those objects into 4 equal piles. And I guess I could do that, right? That each of those piles just gets none. 0 in here, 0 in here, 0 in here, 0 in here. 4 equal piles, each one containing 0 objects. So we can do 0 divided by 4, that's just 0. If I want to take no things and divide them equally among 4 piles, every one of those piles gets 0. So 0 divided by 4 is 0. Similar to this, but different, is if I try to do 4 divided by 0. Now I have these 4 things, and I want to put them in 0 piles. What? I have to put them in no piles at all? But they're already in a pile. How am I going to put them in 0 piles? Anybody remember what happens when we try to divide by 0? What the result is called? Excellent, Moyla. That's exactly right. It's undefined. Very good. And that's probably where the other folks were going to. This is undefined. We can't divide by 0. Dividing by 0 is not allowed. And the idea is there's no way for me to take these 4 things and put them in 0 piles. I can't do it. They're already in 1 pile, so I can't put them in 0 piles. So it's a very important distinction to make that 0 divided by a number is 0, but anything divided by 0 is undefined. Make sure that you're confident in the distinction between those two things. Dividing by 0 is not allowed. As we've done with multiplication, addition, and subtraction, let's look at closure. I have a question for you. I'll set up a poll. The set of natural numbers is closed under division. So, what this question is asking us is, if I took 2 natural numbers and divided, I'll always get a natural number back. That system is closed. And it's a true or false question. The set of natural numbers is closed under division. Is it or not? Let's take a look. Remember, if you say true, you should be able to convince yourself that every time I divide 2 natural numbers, I get a natural number back. If you want to say false, you ought to be able to show a counterexample if you were, asked to do that. That's how you made the decision of false, I would hope, was that you found a counterexample that made this a false statement. I do think trying numbers in questions related to closure is a really good idea. It paints a better picture. Sometimes working in the abstract can be a little difficult. Heck, we saw that back in section 1.2 when we were shading Venn diagrams. A lot of times the abstract nature of that could be challenging. And if you just are natural numbers closed under division? Gosh, I don't know. Start putting some numbers in there, and all of a sudden, hopefully it becomes a little more clear. We'll go another 15 seconds and then talk about this one. Okay, not unanimous, but darn close. All right, let's take a look at this. So what we've got here is a set of natural numbers is closed under division. Now, is it possible for 2 natural numbers to be divided and stay closed? Sure, if I do 4 divided by 2, I get 2. Those are all natural numbers. But if I flip that around and I do 2 divided by 4, now it's natural number divided by natural number, but what I get is not a natural number. So natural numbers closed under division? No, that's false. And right here is my counterexample to prove it. Because I did natural divided by natural, and I got something that was not a natural number. Are there any questions on that? Before we move on and start talking about the standard algorithm. Okay. Standard algorithm for division. If we want to do 825 divided by 5, one way to think of this is that I have 825 items, and I want to divide those into 5 equal piles. How many of those are going to go into each pile? That's absolutely one way to think about what division is about, is I want to divide these in a way that they go into 5 equal piles. As we look at our standard algorithm for division, just like we did with our other standard algorithms, we're going to spend a little time talking about what's going on in each step. And standard algorithm for division is what you might call long division. 5 into 825. So notice here, we're dividing 5 into 825. It's 825 divided by 5. We're 5 divided into, I'm going to write that down. This is 825 divided by 5. That's a perfectly reasonable way to say what's going on here. Or we could say 5 divided into 825. What we wouldn't say is that this is 5 divided by 825. That would be wrong here. So this isn't 5 divided by 825. This is 825 divided by 5. It could be written as a fraction or with a division bar that way. 825 divided by 5. That would mean the same thing there. Or we could say 5 divided into 825. But be careful not to use this language because that's no good. 5 divided by 825 would be the other way, which that's not what we're after here. So be careful about that language. Let me clear this off and make some space. Okay, now let's do our standard algorithm. The way we do this, we actually start with the biggest number. A little more intuitive than we start with the ones a lot, but here we're going to start with the biggest number. This 5 going into this 8. So when I have this 5 going into this 8, keep in mind what we're really saying here is not necessarily 5 going into 8, but 5 going into what? What does that 8 represent? And I won't ask you this every time, I promise. But what does that 8 represent? Excellent, Nicole, Boylan, Jessica, perfect, 800. So really what we're saying here is how many times does 5 go into 800? We look at it from a mechanical standpoint of how many times does 5 go into 8, and it goes once. Notice that 1 is in the hundreds place. So what we're saying is 100 5s will go into 800, or 5 will go into 800 100 times. That's what we've written down here by putting it in that place value. Place value matters. That's why we put that 1 where we put it. Okay, and then we do 1 times 5 and put the 5 down here. Essentially what we're doing, and you'll remember this from when we were converting numbers from base 10 into another base. What we're doing here is we're saying, well, 1 times 500, or excuse me, 100 times 5 takes care of 500. We still need to see how much we have left that we have to distribute. Very much like when we were converting to other bases. We're going to subtract this 5 off. We're really subtracting 500. And we put that 3 down here. And then we say, okay, 5 won't go into 3, but 5 will go into this 32. Really, this isn't really 32. What is it? Because of the place values. Outstanding. You guys are good. Very good. Leslie, Jessica, Moyle, perfect. That really represents 320. And 5 will go in there 6 times. And essentially what we're saying then is 60 times 5 will go into 320. We don't really talk about it that way, but that's what's really happening here. And then that 6 times 5 will be 30. And then we'll subtract what we have left. That 2 comes down. And then we bring this 5 down. We still need to take care of those 5 ones. And this 5 will go into that 25 5 times. And we can check just to make sure 5 times 5 is 25. And that finishes us off. It's not critical to know all the way along that that this 1 represents 100, this 5 represents 500. This is really 320. And so 60, because it's in the tens place, times 5 is 300. And that's why we still have 2 tens left over. But it is really good to know that those things are happening. It's not critical to know that that's what the numbers represent all the way along in order to do these correctly. But I do think it's kind of helpful sometimes to realize that place value has a significant role in what we're doing in these questions. I think it's why it's important when we have kids do this, that they put these numbers in the appropriate place values instead of just kind of putting them willy-nilly up there. Any questions about the standard algorithm for division? Okay, very good. Let's talk about estimation a little bit. Estimation with division has a couple of different techniques that we can go into. One of those is rounding up. What I mean by that is if we want to do 489 divided by 19, I can't do that. But you know what I could do is I could round this up to 500 and round this up to 20. And now I've got numbers that they're both a little bit bigger than what I started with. So I made both of them bigger, so it's going to be pretty close. And now I have something I could do in my head. I don't have to. I can do 500 divided by 20 on the calculator. But you know, if I divide 500 by 10 and I divide 20 by 10, now it has the same value as it had before. And now I can do it in my head and wind up with an estimate here of 25. And that's just a technique for division that 489 divided by 19, there's no way I can do that in my head. But if I round them up a little, make them into somewhat compatible numbers like those, they're easier to work with. And then since they both have a 0 in the ones place, I can divide both of them by 10 to turn them into something that's very easy to work with. And now I have an estimate of 489 divided by 19. Just for the record, 489 divided by 19 is 25.7. So this is a pretty good estimate. Then we look at compatible numbers again, and 4,132 divided by 7. Wow, I don't know what that is. You might think, well, how about 4,200 divided by 10? Well, that's not so bad, because then you can divide both by 10 and have 420 divided by 1, and we get a ballpark of 420. That's not so bad. That's more like the rounding up approach that we did before. So I do want to show you a different way you could do this one if you wanted your estimate to be a little more accurate. What you could do instead of taking that to 10 is you could just go 4,200 divided by 7. Because we know that just sort of off here to the side, we know that 7 times 6 is 42. And so if 7 times 6 is 42, then 7 times 600 would be 4,200. And then that gives me an estimate of what 4,200 divided by 7 could be. That felt a little circular. I hope it's okay. Basically, you could certainly do the rounding up method and work with multiples of 10. Those are always nice. But if you want a more accurate estimate, you could instead leave this 7 alone and just take this to a number that you know 7 would go into nicely. And since 7 will go into that 42, 7 will go into 42 6 times, and so it's 600 is our estimate. Hopefully that's comfortable. If it's not, you can let me know. You can ask questions about what we did there. But that's basically the way that we're going to look at estimation. This division section is pretty short. I thought it might be. All right. Missing digits problems. These are kind of They can be fun. They can also be kind of frustrating depending on your approach. What we want to do is fill in the blanks with something that works. And yes, this is a trial and error problem. And I know trial and error, some people really liked it back at the beginning of the semester, and some people not so much. This is trial and error, but we can have a strategy here. And I'm going to ask you about that strategy. I'll give you the hint. We want to look at the ones digits. So as I look at this and I'm dividing, there's another way I could write this problem so that it was multiplication. I could rewrite this as a multiplication problem so that instead of 4 blank blank 2 divided by 80 blank, that if I multiply both sides of this by 80 blank, those will cancel, and now I have 4 blank blank 2 is equal to 48 times 80 blank. The reason we would do that is because if we're going to do trial and error, I think for almost everybody, trial and error is going to be easier to do with multiplication than it's going to be with division. Okay, so now I want you to think with me here. 4 blank blank 2 divided by, 4 blank blank 2 equals 48 times 80 blank. And we want to know what goes in those blanks. My suggestion to you is use the ones digits. So here's what I mean by that. What I mean by that is if I put a 1 in here, can that work? When I multiply 48 times 81, is it all possible to get a 2 in the ones digit? And why not? Why or why not? So the ones digits are a powerful force here. And if I put a 1 over there, the ones digits that I'm multiplying are 8 times 1. And if I do 8 times 1, I'm going to get an 8 in the ones place. So that's no good. I want to make sure that makes sense before I go forward with it, though. Because my next question to you is, what is going to work? Not necessarily what's going to give me the right answer here, but what's even possible? What could possibly work over here? We're going to let these take care of themselves. We're going to focus in on this spot right here. What is it that I'm going to multiply together that's going to give me a 2 in the ones place? A 4 from last year, a 4 from last. Well, let's see. So if I put a 4 here, when I go to multiply these and I do 48 times 84, 8 times 4 is 32. Hey, look at that. I got a 2 in the ones place. And so they were exactly right. That 4 worked. And probably the way you got there is you went through this and said, okay, well, a 1 times 8 is 8. That's no good. 2 times 8 is 16. That's going to put a 6 in the one place. That's no good. 3 times 8 is 24. That's no good. 4 times 8, though, that's 32. And then if I try this and I do 84 times 48, I get 4032, and I have a right answer to this question. My question to you is, would anything else work? I'm going to give you a couple of minutes to play with it. And that's kind of what these questions are. We just play with them. We're just playing with the ideas of multiplication and division and place value and ones digits. Will anything else work? We've got a proposal for 9. Well, let's take a look. I'm going to assume then that 5, 6, 7, and 8 didn't work. Let's see if 9 does. Let's see, is 9 even possible? Well, let's see, 9 times 8 would be 72. So sure enough, that works in the ones digits. Let's see. Well, 48 times 89, 4272. Well, look at that. That worked also. So this particular fill in the blank had two correct answers. Either one of those would be considered correct, whether you put a 4 in here or you put a 9 in here. But the idea is we're gonna do trial and error, but we do have a strategy. We're just focused in on the ones digits to make sure that what we get works in the ones digit, because if it doesn't work in the ones digit, then it's not going to work at all. I guess also don't forget, the very first thing we did here is this was proposed to us as a division question. We said, I don't like that division question. I'm going to turn that into a multiplication question and go from there. Because generally it's easier for most of us to think about trial and error in terms of multiplication than it is with division. There are a couple of problem types in this section that lean into some vocabulary a little bit. We only have a couple of problems left to look at today, actually. The division section is pretty short, but these are a little bit complex, so I want you to be careful with these. And there's a lot of language in here. If you divide a number larger than 90 by a positive number that is less than 3, what can you tell about the relative value of the quotient? Now, sounds like a SAT question. There's a lot going on in there, so let's talk through this. If you divide a number that is larger than 90 by a positive number that is less than 3, what can you tell about the relative value of the quotient? Now, relative value, we will discuss what's meant by that little piece right there. But first thing we need to do is quotient. The quotient is the answer to a division question. I don't know if we've talked about this in the other, when we talked about the other different operations, but when we add two numbers, what's it called? When we add two numbers together, what do we call the result of that? Excellent, Natalie. Moylan, that's right, the sum. How about when we subtract two numbers? Very good. Difference. What is the difference between the two? Well, we get that when we subtract. How about when we multiply two numbers? What do we call the result of that? The answer to our multiplication? Very good. All right, Xochitl, you're exactly right. We call that the product. Very good. You guys remembered those. So when we add, we call it the sum. When we subtract, we call it the difference. When we multiply, we call it the product. And when we divide, we call it the quotient. So when we divide two numbers, we call the result of that the quotient. And so here, what this is saying is if you divide a number larger than 90 by a positive number less than 3, what can you tell about the relative value of the quotient? And the way that we're going to approach a problem like this is we're going to start by looking at the numbers they gave us, which are the 90 and the 3. Let's just say we divide 90 by 3. So we're going to kind of take a piece of this. We're going to divide 90 by 3. That's going to give us our baseline. So we're going to do 90 divided by 3, and that's 30. So 30 is kind of our baseline. So when we're asked about the relative value, it's going to be compared to 30. Compared to 30, what is our answer going to be? And so my question to you is this. If we divide a number larger than 90 by a positive number that is less than 3, what do we know for sure about the answer we're going to get? And you might not have an answer yet, and that's okay. We're going to talk through it. If you do have an answer, that's awesome. But compared to 30, what can you tell me about the answer we're going to get if we divide a number larger than 90 by a number that's less than 3? How's that going to compare to 30? Here's the way I want you to approach this. It's perfectly fine if you're not sure yet. The way I want you to approach this is try some numbers. So let's try a number larger than 90. How about 92? And we want to divide by a positive number that's less than 3. How about 2? So if I do 92 divided by 2, I get 46. Okay, so if I divide a number larger than 90 by a positive number less than 3, check, check. What can I say about the relative value of the quotient? Well, it looks to me like it's going to be at least 46. That seems reasonable. I don't know if I went bigger and smaller, right? If I did 93 divided by 1, I would get 93. Okay, so my at least 46 still holds. Is at least 46 going to be good enough? Is there anything I could do, some number larger than 90, some number smaller than 3, that would give me something that's not at least 46? And I want you to be nitpicky here. I want you to tell me why this is not good enough, because it's not. Somebody tell me something larger than 90, something less than 3 that would give me a result, a quotient that's smaller than 46. And if not, that's okay, because this is a strange type of question that we've got to get used to. We've got to get our feet on the ground with these. "91 divided by 2. That's an excellent example. If I do 91 divided by 2, I get 45.5. Oops. Well, that's not at least 46, so that blew at least 46 up. And how about if I go kind of obnoxious here? What if I go 90.0001 divided by 2.9999? I've met the conditions. A number larger than 90, yep. A number less than 3, yep. Well, what do we get then? 90.0001 divided by 2.9999, and I get 30.001, and that keeps going. So when I did a number larger than 90 divided by a number smaller than 3, I got that. I could add more zeros in here. I could add more 9s on there. So this is a really hard question. If you don't get it, it's okay. What can you tell me about the relative value of the quotient? If I divide a number larger than 90 by a number less than 3, it's always going to be larger than what? And I don't think this is an easy question. If you don't have it yet, that's okay. But if you do, that's awesome, and I want to give you that chance. Outstanding, Leslie. That is perfect. It's always going to be larger than 30. I want to go back and look at our baseline here. Our baseline was a number larger than 90, a number less than 3. So we use those to establish our baseline of 30. And then if the number on top has to be bigger than 90 and the number on the bottom has to be smaller than 3, then the result has to be larger than 30. It has to be greater than 30. It could be awfully close to 30 like this one was, but it has to be bigger than 30 because 90 divided by 3 gave us this as our baseline, and then we made this number bigger and we made this number smaller, so the quotient has to be bigger than that 30. I'm going to give you a chance to practice one of these, but you can let me know if you have questions about it while we're still here. All right, let's practice one. I'm going to set up a poll for this. If you divide a number that's smaller than 28 by a number that's greater than 7, what can you tell about the relative value of the quotient? And I need to add a word in here. If you divide a positive number smaller than 28 by a number that's greater than 7, what can you tell about the relative value of the quotient? It wouldn't change the answer if I didn't have positive in there, but I think it just gives you a framework to use numbers for examples. I'm going to make a poll for this, and you try it. I don't think these are easy, but I do think you can master them. I'll give you a little time on this because it might take some experimentation and some practice. It might not. Throw some numbers in there if you need to. You might not need to. You might be comfortable evaluating this and reasoning it out. But I'll be very patient on this. Like I said a couple times, the division section's pretty short. We really just have one more question I want to talk about. So we'll take our time on this one. All right, let's take another 20 seconds on this one, and then we'll talk through it. Okay, not unanimous, but strong agreement on less than 4. All right, let's take a look. So the first thing we want to do when we see a problem like this is sort of establish our baseline. And what it says to me here is if you divide a number smaller than 28 by a number greater than 7, what can you tell about the relative value of the quotient? So the first thing I want to do to establish my baseline is do 28 divided by 7 and I get 4. So 4 is sort of my linchpin number here. That's it. I'm looking for something that's either equal to 4, greater than 4, less than 4. But 4 is going to be the thing that the relative value. When I'm talking about the relative value, I'm talking relative to 4. All right. So now I go look at the conditions of this problem, and it says a number smaller than 28. Okay, well, a number smaller than 28, that could be 27. By a number that's greater than 7, well, I'll use 9 because it'll go nicely into that 27, right? So I just did a number smaller than 28, and I did a number greater than 7. Let's see. My conditions are smaller than 28, greater than 7. I got those conditions met, and then that comes out to an answer of 3. So I just did it with a number smaller than 28, greater than 3. And I got a number that is less than 4. That might be enough to convince you right there, because that's the correct answer, and that's it, and we're finished. If you really want to convince yourself, well, yeah, but what if it has to be 3 or less? Because I don't see anything bigger than 3 here. All right, well, let's try the number that's as close as possible to 28. Let's try 27.99999. And I want something greater than 7, but as close as possible to 7. How about 7.00001? If I divide those, what I'll get is 27.9999. How many did I do? 5 divided by 7.00001. And I get 3.999999. And now I can see that if I get as close as possible to those numbers, I get something that is less than 4. 4 was my baseline, and because I made this number smaller and I made this number larger, that means I have to come up with an answer that's less than 4. That was the most common answer on this one, which is really good. And hopefully that was sort of the approach you took. You didn't have to use 27 and 9. You could have used, a number smaller than 28 that's greater than 7. You could have said a number smaller than 28, a number greater than 7. Okay, and I still get an answer less than 4. And every single time I'm going to get an answer that's less than 4. That's my baseline. And if I increase the top and decrease the bottom, the quotient is going to get smaller. That's the idea here. I don't think those are easy, but I think with practice, we can get the hang of it. It looks like we're doing pretty well. Let me know if you have questions on that. There's one more I want to try with you today, and it actually is not quite as difficult as the ones we were just looking at. Amy is making bracelets. Each bracelet that she makes uses 3 red beads and 7 yellow beads. She has a package of 25 red beads and a package of 45 yellow beads. And my question to you is, how many bracelets can she make? I'm going to set up a poll for this. We don't have to be in a hurry. Don't overthink this, but use your problem-solving skills to reason this one out. We'll go another 20 seconds and then talk about this one. Okay, almost unanimous. Very good. That's kind of how I expected this one to go. We'll talk about it just to make sure we're all on the same page. So essentially what we've got here is that Amy uses 3 red beads and she has 25 of those. So if we do 25 divided by 3, when we do that, we'll get 25 divided by 3, 8.333. What we care about is how many bracelets can she make. Well, with the red beads, she could make 8 bracelets. However, she also has another color that we've got to work with here. She uses 7 yellow beads every time she makes a bracelet, and she has a package of 45 of those. So we'll do 45 divided by 7, and when we do that, 45 divided by 7, 6.43. So with the yellow beads, she can make 6 bracelets. Well, she needs both. The key here is the smaller is our limiting factor. So while it's true that she has enough red beads to make 8 bracelets, she only has enough yellow beads to make 6. So the number of bracelets she can make is 6 because the yellow beads are her limiting factor here. So she can only make 6 bracelets. Let me know if you have questions about that. A couple of things I want to say about your homework before we finish up today. If you see the term break even in your homework, that means there's no profit and no loss. It's just 0. There wasn't any profit, there wasn't any loss. It's just 0, even. In here, you might see some modeling review from chapter 6 where you're going to need to write an equation or an inequality to represent a real life situation. That's okay. It's something we've done before. I think you're probably going to be pretty comfortable with it. So that we all get the same answer, I know back in chapter 1, there were some problems where we just sort of left it open-ended. Like, depending on the assumptions you make, you might get a different answer from someone else. I thought that was great back in chapter 1. Now I'd rather sort of focus us in so that we all have the same answer. We're all pointing in the same direction for this particular problem anyway. In number 29, use an 8-ounce glass because it asks how many glasses could you do. Well, it depends if you use a 6-ounce glass or an 8-ounce glass or a 12-ounce glass. But so that we're all working towards the same thing, use an 8-ounce glass for number 29. And then number 31, we've come across problems from time to time that they're just for fun. It's not something I would ask you on a homework or a quiz or an exam. Well, I guess I would ask it in a homework, not on a quiz or an exam. It's just for fun. But you could try that one and see how it goes.